Hello, this is Miss. Here are your answers. Happy configuring! Miss Heaton. We're going to talk today about electron configurations, and this is from chapter 11.9 and 11.10 in your textbook. The first thing I want to do is review real quick some parts of the Schrodinger or quantum mechanical model that you are hopefully already familiar with. We have talked already about the shapes of the orbitals. We've talked about s, p, d, and f orbitals. You're already familiar with those shapes. Now today we're going to simplify things and not represent them with these pictures. Instead we will use a box to represent each orbital, because it would be really hard to draw these pictures every time. What you do need to remember is that the s sublevel, an s orbital can hold 2 electrons. Remember, every orbital can hold just 2, but p's, at a p sublevel, you have 3 orbitals, so that would hold a total of 6 electrons. A d orbital can hold 2 electrons, but d sublevels have 5 orbitals, so there'd be 10, and f's can hold up to 14. This is going to become important because what we're going to do today is talk about where each electron lives. How does it know which orbital to go into? And this is going to become important for bonding, so we're going to learn about the electron configuration rules. And there are 3 rules that the electrons must follow in order to find their home in an orbital. The first rule is the Aufbau principle. This is kind of like the lazy tenant rule, so this is kind of a informal name for it. The proper name is the Aufbau principle, but Aufbau means build up. And it's kind of like if you are renting a place or looking for a place to rent, you are a tenant, and if you are lazy and the apartment building you're looking at has no elevator, if you're lazy, are you going to take the room available on the first floor or the room available on the second floor? Obviously you don't want to climb those stairs if you don't have to, so you're going to take the first lowest room available. Electrons are the same way. They're going to fill the lowest available energy orbitals first. So over to the right here we see a diagram that illustrates the order that the orbitals get filled in. The lowest energy is 1s, then we have the 2s, then the 2p, then 3s, 3p. Oh, this is kind of weird. The 4s happens to be very slightly lower than the 3d, so it would fill first, and so on. Now, do not write this down, do not memorize this, because I'm going to show you later an easy way to remember the order of the orbitals that get filled. Rule number 2 is the Pauli or Pauli exclusion principle. This rule says that each orbital can only hold up to 2 electrons, but they have to be spinning in opposite directions. You could kind of think of it like a top spinning clockwise or counterclockwise, but we'll show this each electron as an arrow. So this is an electron. This one's spinning up, this one's spinning down. Rule number 3 is Hund's rule or Hund's rule. This could be informally called the empty bus seat rule, because if you get on a bus and you have 2 options of places to sit, you could either sit by the big smelly guy or you could sit by yourself. What are you going to pick? Obviously, you'll pick to sit by yourself. Electrons do the same. So if there's multiple options of orbitals at the same energy level, at the same sublevel, so like if you have a set of 3p's or 5d's or 7f's, you're going to put 1 electron in each orbital before they start pairing up and spinning in opposite directions. So here's 2 options for putting 4 electrons into a p orbital. I want you to figure out which one is correct. On the left we have 2 and 2. On the right we have 2, 1, and 1. Well, if we're following Hund's rule, the one on the right would be right, because those electrons spread out and filled up each orbital represented by a box before they paired up. Okay, so let's start applying those 3 rules. Oh, actually, you know what? I have a little trick to tell you. Like I said earlier, you don't need to memorize these rules, these orders of the orbitals, to figure out what will fill next. All you have to look at is your handy-dandy periodic table. We haven't done a lot with this yet except find molar masses from it, but it works out really well that electron configurations correspond to different positions on the periodic table. So you'll want to have a periodic table handy for this next part, and in fact you'll want one that you can write on and label each section. If you don't have one, at least draw a sketch of the periodic table with the correct number of columns in each area and label that. So the first thing you should label is down the left-hand side. Label each row 1, 2, 3, 4, 5, 6, 7. This corresponds to the energy level of the electron. Each row is an energy level. Now there's this weird thing, I don't know if you've noticed this, but on your periodic table the numbers jump in this section here, because these blocks actually fit in the middle of this green section here. It's kind of like how Hawaii or Alaska is drawn on the US map kind of in the corner. They say actually it belongs 7,000 miles that way. Same thing here. This would be kind of part of row 6 and 7. Now, each set of columns on the periodic table actually corresponds to a sublevel. So this area here we call the S block. It's the S sublevel. So electrons, the last electrons that go here belong in the S sublevel. And that's easy to remember because there's 2 columns and 2 electrons fit into the S sublevel. Over here, these 6 columns are the P block because 6 electrons fit into the P block, or into a P orbital set. This block here is called the D block. There are 10 columns. And down here we have 14 columns in the F block. Now, there's kind of a weird thing here. These D blocks are actually off by 1 number. So rather than being the 4 row here, this would actually be the 3D. And this row would not be the 5D, this would be the 4D. And I'll show you how those orders go in just a second. Real quick though, I want to show you how this F block fits into the middle of the periodic table. So this is what the periodic table would look like if we included the F block where it actually belonged. That makes it really long and skinny and hard to see. So instead we put those down at the bottom and say, see the bottom for the right answer. Okay, so how does this apply to electron configurations? Well, remember we had that whole order of orbitals. So let me show you how each coordinate on the periodic table tells us what orbital gets filled. Remember, orbitals get filled from lowest to highest energy. So we'll start by filling up the 1s orbital, then the 2s and the 2p, 3s, 3p, 4s, 3d, 4p, and so on. You may want to label those on your periodic table as well. Notice that the 6s fills, notice the 6s fills before the 4f, and then we jump back to the 5d, 6p, 7s, 5f, 6d, 7p. So you're going to get really comfortable using this to help you figure out what order the orbitals are going to fill for your electron configurations. One other thing I should point out is that helium and hydrogen are kind of misfits in some ways. They can float back and forth between which side they fit on, and for electron configurations, helium kind of belongs over here next to hydrogen. So you can imagine that helium fits right here. It's part of the S block. Okay, so let's talk about how you would represent an electron configuration. Whoops, wrong thing here. So let's look at hydrogen. Electrons from hydrogen, there's only 1, right? Because the number at the top, the atomic number, says 1. So there's 1 electron in hydrogen. So it's going to fill the lowest energy level first. It's going to fill the 1s orbital first, because it's in the 1s block. So the 1 tells you what period, what row you're in. The S tells you what block you're in. You're in those columns. And the exponent here tells you how many electrons belong in that orbital. And we're only going to put 1 electron in that orbital because we just have 1 electron. Here's another example, oxygen. Find oxygen on your periodic table. It has 8 electrons. So what we're going to do is draw the box diagram first, because I think that's a little bit easier to see. So remember, each box represents 1 orbital, and each orbital can hold 2 electrons. The first box that we fill, electrons 1 and 2, belong in the 1s orbital. So we'll put 2 electrons there. And you can either draw half arrows or full arrows. So after those 2, then we'll go over here and put electrons 3 and 4 into the 2s orbital. So draw those 2 arrows. After electron 4, we'll jump and put 5, 6, 7, and 8 into the 2p orbital. Now remember, p orbitals occur in sets of 3, and each orbital can hold 2 electrons. But we only need to put 1, 2, 3, 4 electrons in there. So we need to follow the empty bus seat, or Hund's rule, by putting 1 electron per box before we pair them up. So that would be our box diagram for oxygen. And we can represent that in a different way, without drawing the boxes, as our electron configuration that we did like for hydrogen. So we'd say in the 1s orbital, there are 2 electrons. In the 2s orbital, we put 2 electrons. And into the 2p orbital, we put 4 electrons. So this would be the electron configuration for oxygen. And you can check that you're correct by adding up the total number of exponents, and it should add up to the atomic number, or number of electrons, in your element. And in this case, 2 plus 2 plus 4 adds up to 8. Okay, let's try one more example. Calcium. Calcium is right here. It is atomic number 20, so it's got 20 electrons. So what we'll do is we will start with our first 2 electrons. They automatically, because of Aufbau, go into the first s orbital. We'll put 2 electrons there. Then we'll fill up the 2s orbital with electrons 3 and 4. Then we go over to the 2p and put electrons 5, 6, 7, 8, 9, and 10 into the 2p orbital. So we'll follow Hund's rule, put 1 per box before we pair them up. So electrons 11 and 12 would go into the 3s orbital. Electrons 13 through 18 would go into the 3p orbital. Oops, that one ended up with really wide boxes. And then finally, we'll put 2 electrons into the 4s orbital. So that would be our box diagram for calcium. And the electron configuration would be very similar, except we would just write the electron number as the exponent instead of as the arrows. So this would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now, what you're going to notice the more you do these is that there are lots of patterns that emerge in the periodic table. The first is that each row has the same highest occupied energy level. So any element that's in the same row of the periodic table has the same last energy level, except D's and F's are off by a row, or 2 for the F's. The column number, the group number, tells you how many total valence electrons there are. Now we haven't developed this idea a whole lot yet, but this is like the outer electrons, and these are going to become important for bonding. And finally, if elements are in the same column, they're going to have the same number of electrons in their outer sublevel. So for example, if we're looking at the periodic table, let's get our periodic table back here. All of these elements are going to end with something S1, and all of these are going to end with something S2. Again, the more you do this, the more you'll see those patterns emerge. Okay, here's your assignment. You need to write out the orbital box diagram and the electron configuration for iron and bring that to class with you. Finally, if you can do these 4 points, you are good to go on this concept. So first of all, do you know the 3 rules for electron configurations? Do you know how to use the periodic table and those rules to determine the electron configuration? Can you write orbital box diagrams? And can you write electron configurations? Now, we're going to practice with some harder ones in class, but if you can do the basic ones, you are ready for class tomorrow. Finally, some of you have asked for a little bit more practice, so here's 2 problems that you can try. So take a minute to try those if you would like. Hit the pause button because the next thing you're going to see is the answers to these problems. So I hope you all have a great time configuring.